Hi everybody out there. Good afternoon. This is the Iris Score Program webinar for the last week of May, and this is Andy Frisetto broadcasting live to everybody out there from the Iris headquarters office in Washington D.C. For those of you who aren't familiar, the Incorporated Research Institutions for Seismology is a nearly 30-year-old nonprofit consortium of universities, and it's also a science facility that's funded by the National Science Foundation to operate programs on its behalf that enable a broad spectrum of geophysical research, primarily in seismology. If you haven't met me personally, I'm the IRIS project associate. I call myself a Swiss Army knife of sorts that helps to manage the EarthScope US array, the global seismic network, as well as some of the other seismology research programs that are housed here. The webinar series is sort of an additional perk of this job that was initially developed to highlight science done under these programs, but it's expanded to include a wide variety of topics. Just to highlight that, if you're interested in checking out some of the previous webinars, you can go to www.iris.edu/HQ/webinar. You can see it up on the broadcast screen here. And this is going to get reformatted soon with our website upgrade, but it'll be pretty similar in format where we have our upcoming webinars listed at the top. And then you can scroll back in time and look at the thumbnail for various past presentations. Click on the thumbnail and it will take you to YouTube where you can watch these previously and they've been archived. So just as an outline to how these work, if this is your first webinar, so during the webinar, it'll be only the speaker and I who are unmuted. So today's speaker is Paul Richards, and as soon as I finish the introduction, I'll turn it over to him. His audio will open up and the presentation will go on from there. As the webinar goes ahead, if you have a question related to either anything technical in the webinar that might be urgent, if you can't hear the speaker that well, or if you can't hear me, or if you have something related to the presentation, just type it into the question box on your webinar control panel, and I'll see those immediately, and then I'll step in if needed. Otherwise, any questions that are related to the content of the presentation, I will discuss with Paul after the presentation is finished. At the end, I will just read your name and your question, and those will be answered one by one. If there's a redundant question, since nobody knows what questions are being submitted as the webinar goes on, if there's something redundant, I'll probably just skip past it if it's already been answered. There's only been one occasion where the webinar has had what I would call a catastrophic glitch. So if that happens and you get kicked out of the webinar, just give it a second and I will reset things on this end and then click on the link in your email and that'll take you right back into it, hopefully as if nothing happened. Both the presentation that's going to be happening in a moment and the questions that I go through afterwards are being recorded, and those will be posted on the website as the previous ones have been before. And just as on a sort of survey note, it helps for me to know if there's anybody out there that's watching this as a group of people. If there's a few of you in a lab, just to keep a record of all the extra viewers beyond just who registered. So if that's your case, just send me a note afterwards, or send me a note in the question window, and just let me know how many people are watching remotely at your location. So I think without further ado, I'll turn it over to our speaker. So just to finish my introduction, our speaker today is Dr. Paul Richards. He's a professor emeritus at Columbia University, and he's worked primarily out of the Lamont Doherty Observatory. Paul's originally from England. He received his master's and PhD from Caltech, and he spent over 40 years at Columbia. Among his many internationally recognized achievements in the field, with Kayaki, Paul co-authored basically the book on seismology, quantitative seismology. I'm also personally happy to welcome Paul today. He presented the first geophysics lecture that I actually ever attended, which was when I was a freshman at the University of South Carolina in fall 2000. So I think without further ado, our speaker today is Paul Richards, and he will be talking about methods of seismic monitoring for underground nuclear explosions, past, present, and parentheses, maybe future. So Paul, I'm going to turn over presentation control to you. And once that happens, it'll enable your audio. So 1 second. All right, so we should be able to hear you now, Paul.
Okay, Andy, thanks for that introduction. Indeed, I do remember that time of, you say you first heard me way back in 2000. I think I was a Phi Beta Kappa lecturer in a number of campuses. So today the story about seismic monitoring of underground nuclear explosions, I hope to show, has all sorts of wider implications in our own very specialized field, because in my opinion, the modern capability of seismology to monitor both nuclear explosions and earthquakes and other interesting phenomena besides is actually taken to the level it is because of this national security need that's there in my title today. So I have a lot of people to thank, my colleagues as Lamont, to people I've worked with internationally and nationally, and to participants in the annual monitoring research reviews, which have been conducted most years since 1960, and it's a record of more than 50 years, of which the last 30 or more have been unbroken, except unfortunately not to have such a review this year. If I were to thank all the people who helped me here, I'd be reading names for the most of my time. So if you'll excuse me by pressing on, I'm speaking only for myself. I'm the only one who should be blamed for what is to follow. And let us begin with a key year, 1958. I'll come back to why that year in a minute, but this was the time in which seriously the concept of seismic monitoring for underground explosions began, at a time when in all the previous time there'd only been one underground explosion, Rainier, at the Nevada test site. And at the meetings of a rather strange format in Geneva, trilateral between the USSR, the USA, and the UK, the idea of how to monitor in the context of providing the technical support for a proposed comprehensive ban on all nuclear testing led first to proposals from each delegation, as you see them listed here. From the Soviet side, on the order of 100 control posts. For the US, 2 people, not speaking for the whole delegation, but contributed a report on the need for far more than that. But the third system was the one that gained some traction, proposed by the British group. And so William Penny suggested 160 to 170 land-based control stations, conceptually each of them an array, to be supplemented by 10 ships. So this was a meeting in which certainly nuclear weapons scientists had a major role, but there were, as you see listed here, 3 US seismologists present, Jack Oliver, Frank Press, and Carl Romney. And in the discussions in Geneva, this Penny system was quite well received. Here is a version of it. Let's see, on my screen, I see, more than I need to. Let's get rid of this. Okay. So you see a conceptual version of the 170 control posts, which quite remarkably, 50 years later, we have more or less today in the international monitoring system, or the CTBT, seismic only, where the total, first of all, for a primary network of 50 stations, all the time with data being scrutinized, is supplemented by another 120 stations whose data can be interrogated to clarify anything that the primary network brings to the attention of analysts at CTBT headquarters in Vienna. So going back then to this proposed Geneva system, it was understood at the time that there would be the need to work with both teleseismic and regional signals. And here, from a diagram Carl Romney generated in 1960, and probably even earlier for the negotiations, we see conceptually the way in which amplitude falls off rapidly with distance over on the order of 1,000 or so kilometers, and then teleseismic waves, those going much deeper in the Earth, begin to emerge on the order of 1,500 kilometers away from the seismic source, and then can be monitored essentially all over the world. So in this diagram, how to work with both regional waves and teleseismic waves. The regional waves, for example, shown here, propagating as PN, perhaps at the top of the mantle, or as PG waves, which in certain types of geology, shield regions, for example, propagate very efficiently up to 1,000 kilometers or sometimes more, with a notable complexity depending upon the region in which they are propagating, compared to the relative lack of such variability. There's some of it, but not so much in the teleseismic signals. Well, in these first discussions, so much happened in 1958, but the system I've so quickly summarized for you was characterized by its proponent as allowing on the order of 90% of all earthquakes equivalent to 5 kilotons or more to be detected and identified, but that would leave on the order of another 10%, which on the territory of the USSR and China was particularly of interest to the US. But at the time, as the negotiations towards August of 1958 were concluding, at the time this was perceived to be a manageable difficulty. However, later in 1958, the US conducted tests additional to Rainier at the Nevada test site, and the US delegation, looking at the results from these tests, reached much more pessimistic estimates of seismic monitoring capability. There was a lot happening at this time, a lot of explosions in the atmosphere, very few underground, and to make that point, let's see if I can now bring up a very useful video generated by Sao Hashimoto, which simply shows in global view the occurrence of nuclear explosions in the 20th century, not the current century. And let me just play it. It has 1 month lasting for 1 second on the screen. So as you see it here on the top right, it's set up for January 1958. And let's just play it for a minute to see the activity going on at this time. So you see explosions in the atmosphere in the Pacific by the US, and then beginning with the UK. You see a moratorium that lasted for about a couple of years in 1959, and then in 1960 the French began testing in all in Africa. There's the first one, a few more, and then on this scale, a few seconds later, or a few months later in real time, the Soviet Union began a massive series of nuclear explosions. In 1961, here they go, many of them, followed by a massive number of nuclear explosions in the atmosphere by the US. So this was the setting at the time of negotiations, as I began this last 5 years in 1958, up until the end of 1962. So as I say at the bottom of the screen, it was a busy time, And with the hardtack data in hand, the conclusions presented to the US Congress, I will summarize on this screen, but overall they reached such pessimistic conclusions that effectively it became clear that monitoring was just not deemed good enough in the policy-making circles. And the numbers that appeared to emerge would that from the hardtack results extrapolated to earthquakes worldwide, and the fraction of them on the territory of the USSR and China would be on the order of 100 to 500 per year, indistinguishable from 5 kiloton explosions. So that's a pretty remarkable summary statement, and it can be broken down into 3 different steps. How many earthquakes occur each year at different magnitude levels? When would the magnitude levels be successfully monitored? That's to say, down to what threshold could reliable detection and identification be achieved? And then how to relate the magnitude to the yield to get from the seismic summary, an expression of detection capability perhaps in terms of magnitude, into something that would correspond to a yield. So in each of these areas, this key summary from 1959 turns out to, against each of these 3 bullets, a modern understanding. Perhaps it's a little unfair, but with decades of hindsight, we now find that the number assumed in 1939 of about 20,000 earthquakes worldwide each year, a magnitude 4 and above, using a specific magnitude scale, we would give about 7,500 for that number. What would be the capability of a dense global network of the type corresponding to the Penny proposal, which at the time was thought to be reliable down to about magnitude 4 or 4.5. Today we would give about 3 to 3.5 for that magnitude range. And then finally on the magnitude yield relation, the interpretation used in 1959 was, as you see it here, giving a yield of about 19 kilotons for a magnitude of 4 3/4. But in the geology, as we came to understand it, of what became the USSR's main test site in Semipalatinsk, that would correspond to a significantly smaller yield using this, at the end of the screen, magnitude yield relationship. So at the level of earthquakes indistinguishable from 5 kiloton explosions, I think a modern understanding, unfair perhaps to do, but we learned how to do this work of monitoring at this scale, 5 kiloton explosions with well coupled into the ground, as you see in the assumptions on all of the screen. Essentially none of them would be under modern capabilities a problem for seismic monitoring. So let's repeat that these early conclusions had to be developed in a cautious atmosphere based on minimal data at a time when seismology was practiced at very few places. I have to say that at this time, prior to 1960, seismology was a fairly sleepy science. National research support at the level of less than $1 million a year, and it suddenly changed. However, we'll get to that, but in this period, 1960 to 1962, seismology had certainly failed in the negotiation of CTBT, and what resulted was the Atmospheric Test Ban Treaty. Here's its more formal name, signed in August 1963, agreed to ratification in the Senate a few weeks later, and entered into force just a few months after it was originally signed, followed by 1,500 underground nuclear explosions in the 20th century. So, what happened to seismology? The President's Special Assistant appointed a panel which recommended changing the way that seismology was conducted. Almost immediately, annual budgets on the level of about 20 million were outlined, and the funds were actually spent. We got the worldwide standardized seismographic network, we got arrays, support for basic and applied research for decades, and teleseismic monitoring became the standard practice for many, many years. So we came to understand the work in terms of 6 steps. As you see them here in red, detection. One of the hardest is association, given how busy our planet is, so many earthquakes, so many mine blasts on a given day. The work of associating all of the signals that corresponds to a particular seismic event is what is meant by association. The work of location, perhaps one of the oldest technical challenges in seismology, and itself one of the best discriminants, the interpretation of an accurate location, in particular depth, but also epicenter location, is a prime component of identification, although identification does mean certainly more than just location. The question of an event that's been identified as potentially a nuclear weapons test, who did that, attribution, and then related to that, yield estimation. Now, how do we do today? To answer that question, it's helpful to break it up into a couple of steps today. For nuclear tests carried out, as most of those 1,500 underground explosions were conducted, or separately, for nuclear tests carried out with an effort to evade a monitoring system. What can we say about these levels of assessment? Well, let me just review what I regard anyway as achievements, and I'll talk about achievements in 2 modes: in monitoring capability, yes, but also in how the overall work of all monitoring activity, including for earthquakes, has been improved in seismology by this decades-long attention to now doing the work of monitoring nuclear explosions, not just in the context of supporting an arms control objective, but now with another role for decades, to get clues on the actual nuclear weapons development as it was being pursued by potential adversaries from the perspective of one country monitoring the nuclear explosions on the territory of another. Well, achievements. One thing is we do have that international monitoring system and the associated international data center headquartered in Vienna. And here is shown the 90% confidence level as was achieved about the year 2007 with work done here by the NORSAR group, showing that in the northern hemisphere, these are contours, and the magnitude as shown represents the level at which it could be expected with this degree of confidence that 3 or more IMS primary stations would get a detection at the level of 10 dB above the noise. That number, 3 or more stations, being chosen with the fundamental idea that that would be presumably enough at least to get a rudimentary location estimate. So this is a map of detection capability at enough stations to achieve a useful location estimate. Here's another achievement over the last 50 years, although this one took decades to achieve. You see on the very bottom left a magnitude yield relationship. First, I think, developed in technical reports by Jack Murphy, but developed and applied by many in the subsequent decades. In application, this was to the Semipalatinsk test site, and as an achievement, what you see here for each of the years from 1964 to 1989 is in gray the total yield for all of the underground nuclear explosions conducted on that Semipalatinsk test site in that year, compared in black to the number which has been formally announced by the Russian Federation in a number of technical reports that emerged after that period of perestroika and glasnost. And it is quite remarkable, I think, that in each year we see such good agreement. These are linear scales, not logarithmic, and quite remarkably, with very few exceptions, the total is within 10%, as announced, as compared to what would be worked up from the summary. Now, we don't achieve anything like this capability for all test sites, but I put this up simply to show what has been achieved for one of the most well-studied test sites in the world. Let's move right along to the present century, again as an assessment of capability. And shown here is a map pertinent to the first nuclear explosion conducted by North Korea at the location, as you see it here on the left, of a star. And I will show some data from it, but in particular I want to make the point that this very first explosion was really quite small, probably on the order of a kiloton or less, and I will show its signals at an open station in Manchuria at a distance of about 300 kilometers. Blow up on the right, as you see it here, shown also is the location of a number of earthquakes in circles. In the one in particular in red, I'll show you its data too, and in triangles, a number of very small 1-ton or 2-ton chemical explosions. So as an achievement in the year 2006, here you see the vertical records at Mundanjiang, China, of the small nuclear test, of a nearby earthquake, and of record at that same station of a 2-ton explosion. And of interest here is to go back to work that emerged by a number of different research scientists in the 1980s and 1990s. Of course, the hardest work of identification is for small events, and between a small earthquake and a small explosion. As you see it here in the first line, a broadband recording was recognized by a number of different research groups. The plain fact that if one takes the broadband recording and passes it, for example, in a high frequency band, 1 to 10 hertz, or an even higher frequency band, 10 to 25 hertz, that the comparison of the P to S ratio is vastly different for earthquakes than is the case for explosions. So the P to S spectral ratio, small for an earthquake, and here you see very feeble S waves. So the P to S spectral ratio, large for explosions. And in application to specifically the underground nuclear test of 2006 in North Korea, compared to a nearby earthquake, all of these features were well understood before that first nuclear test of the present century occurred. So here we are now in 2013. There have been 3 events at this test site. Here I show the 3 component records. They're remarkably similar for north, vertical, east-west, for each of those 3 explosions. But what is different about the one that occurred this year in February 2013 is, for example, for the international monitoring system, that it has been beefing up its number of operating stations, both the primary network and the auxiliary network. And here you see the number of stations in the international monitoring system that got signals for that test in February this year. Even so, a statement issued, about 96 international stations received data and forwarded them promptly in near real time to Vienna. And a vastly greater number even simply of broadband stations. This is a graphic put together by people in IRIS within a few hours of the occurrence of that last nuclear explosion. So these are achievements that we now have so many stations and communications are so good. Interestingly, looking at that NDJ station once more, here you see about 15 seconds of data comparing the shot in blue in 2009 and the one in red in 2013. And the very fact that there's such a broad frequency band and such a substantial time period, a good time bandwidth product here, we would have to conclude that these two tests were within a fraction of a kilometer of each other. So a more formal process managed by the US National Academy of Sciences reported in March of last year on monitoring capability with an overview statement saying that the 90% confidence limit for detection is well below a kiloton for fully coupled explosions, that seismology is the most effective technology for monitoring, that monitoring capability is improved substantially, and so on. And then going on to more specific aspects of the capability in the context of the possibility of an effort to evade monitoring systems. And this now is an area where certainly the National Academy panel had a consensus. It included a number of experts on radionuclide monitoring, and it included former weapons lab directors. And of course, there's a comprehensive test ban treaty. The possibility exists to conduct very small nuclear yield explosions below the occasional numbers that you see in these images. And then the question of the significance of the possibility of clandestine testing takes us well outside the realm of seismology. So I'm going to go back to other achievements. Let me talk now about another type of achievement altogether, our basic understanding of seismic signals and the institutions that have been built up to provide supportive data for the community that does the work of monitoring and research in earthquake hazards, studies of earth structure, and so on. So, in the last more than 50 years, more than 1.5 million seismic events documented by an international group headquartered in the UK, which receives information, typically phase arrival times and amplitude information, from up to about 6,000 stations in any one year. The US Geological Survey was the subject of one of these IRIS webinars less than a year ago. Gavin Hayes, as you see his title here, reported on 3 main missions of the USGS: to monitor global earthquakes and disseminate information to affected communities, to integrate channels coming in from many different organizations, and to pursue an active research program. I was amazed to learn from Gavin just a few days ago that the USGS, headquartered in Golden, Colorado, at the National Earthquake Information Center, is receiving about 1,500 channels of broadband HZ data in real time, and more than 7,000 channels of data overall from 98 networks. So this is a major asset, not just for the immediate purposes that the USGS has listed, but also for conducting research in monitoring mine blasts, candidate nuclear explosions, a major asset. There's a third way of providing an important data product. I'm happy to mention the so-called, as it began, the Harvard Centroid Moment Tensor project, initiated more than 30 years ago by Adam Swansky, who, with his colleagues, developed ways to characterize seismic sources, most of them earthquakes, in terms of the moment tensor, as I'll shortly describe. For the last 7 years, this project has worked at my home institution, led by Joran Ekstrom and Meredith Nattles. So here you see the way to characterize the force system underlying a point source approach to an earthquake or an explosion. Moment tensor analysis endeavor to figure out the different elements of the moment tensor using, as it does, the global seismographic network operated by the IRIS consortium with the US Geological Survey and a number of other regional and national agencies. So the global centroid moment tensor is now producing results for on the order of 1,500 to 2,000 earthquakes a year. Not only earthquakes, though. Wow, what's that? Well, in April this year, 2013, I think it was April the 11th, a substantial collapse in the biggest open pit coal mine in the US occurred. It's about 4 kilometers across, cracks developed, and this massive flow into the crater, so disruptive. Here's another image, led seismically to an extraordinary set of seismograms. Extraordinary in the sense that here you see their long period representation, and they have an MS at the level of magnitude 5. But in terms of conventional body wave magnitude, certainly well below magnitude 3. So it's an achievement that we have this understanding of not just explosions, not just earthquakes, but other phenomena on our active planet, in this case an anthropogenic source, a landslide that resulted. So world seismicity, these are 25 years of events as you see them, organized on most of them on the fringes of plates, well studied by global centroid moment tensors. Now, I would appreciate if you would indulge me for a minute. I've been a member for many years of the Royal Astronomical Society, and they have a logo. Here it is, and you see a Latin tag around here. It says in Latin, "Whatsoever shines should be monitored." And I've been wondering what might be an appropriate tag for us in our own field to capture in some short phrase the vast array of so different seismic signals, from the very small to the very large, in the sense both of small amplitude and large amplitude, as well as the sense of small period and long period, and the small network and the single station. And a suggestion might be quiquid terram movit notarenter, whatever moves the ground should be recorded. If we can stay with that principle, we will do so well, not only in monitoring for nuclear explosions, but to get a better understanding of the interior structure of our planet and of its earthquake hazards. And let's look at some of these structural studies. So again, achievement of modern seismology. We have these maps of variation in crustal velocities. This is for the crust. It characterizes the variability of the PG phase. Here for subMOVO, the variability of the PN phase. I had this image up before. PN is a very important wave for study for purposes of locating earthquakes and explosions with regional signals. And as we look at these 6 steps, let's ask the question, how can we do this work and improve upon current procedures? What can we do better? Is there something on that list that we can do much better? And maybe it is location. The most basic problem to address. We locate earthquakes, for the most part, using what is called Geiger's method, which was first published in English 101 years ago in 1912. Locate earthquakes one at a time using phase picks. But there's a growing understanding that using an archive of signals, stations of high quality that have operated for decades, it may be possible to achieve a radical improvement in location capabilities. So let's review the problem. Again, these images. Suppose we have a seismic source, and whether it's a PG wave or a PN wave, it goes past 4 stations. Where was the hypercenter? What was its origin time? Well, it's not like that, because the waves don't expand in circles because the Earth has complicated lateral variations. We can't pick the arriving signals accurately, so there's a pick error too. So with this variation and these PN variations, we have, in a sense, a kind of squiffy circle that spreads, and we don't know that model very well. So I turn to some of the results that my colleagues at Lamont, Felix Waldhauser and David Scharf have achieved over the last 6 or 7 years, where my hope would be that they're, to me, amazing achievements in the West, potentially over the next, I hope it's not more than 10 years, can find wider application to monitoring and improving to get highly more precise event locations. Basically, in this part of the world, where there are on the order of 900 stations, as you see them up here, we can find, the work has been done by my colleagues, in a comparison between the catalog and the relocation where the events have been located with respect to their neighbors using cross-correlation to measure relative arrival time, and where large numbers of events have been located at the same time. More detail at this link. This achieves tremendous success, but could it be done not with quite so many stations, but just with a sparse network and using automatic detection? That's the key research question. So as a project of David Scharf's, 10 years or so ago, this work was begun in eastern China. A flurry of earthquakes in Liaoning province, as recorded at 4 stations at far regional distances. The signals from that cluster are remarkably similar. Here you see 2 superimposed seismograms looking remarkably the same, and by measuring the relative arrival time of neighboring events, David was able to achieve highly precise, look at the time scale, locations here with relative errors at the level of on the order of hundreds of meters. Well, could that be done, for example, in California? Well, again, Scharf and Waldhauser have led the way with a recent paper showing that without having 900 stations, just a sparse network, for example, in California, can do an excellent job of getting relative locations in the Parkfield region, except that with this lower station density, it's not a matter of monitoring now to levels of magnitude 0.5 and 1 and so on, but somewhat a little above that, above 1.5 up to 2 and so on. But using the longer wave train recorded at greater distance, that same level of precision appears to be achievable in location estimates. So, cross-correlation methods. Yes, they're very useful to measure relative arrival times, to find repeating earthquakes. Can they be used as a detector? So, maybe. So, David Scharf has shown as an example here of taking noise and adding it at different levels to the same, adding it to with different levels of signal to noise ratio, shows that, yes, that signal, so very clear at high signal to noise ratios, with cross-correlation methods can be pulled out even when the signal is substantially below the noise level. To do that with 3-component signals is to enhance the process. Steve Gibbons at NORSAR has developed cross-correlation extensively as a detector too in the context of using arrays. And in application to a broad region, the question arises with a study of about 20,000 earthquakes, how many of these events that are not repeating signals on top of another earthquake just the same, but are in the neighborhood of other events, what fraction of these events write waveforms that can be used as a template to detect the occurrence of neighboring events? And the preliminary indication is that a lot of them can, on the order of more than half for a time period as studied and as documented by David. So preliminary results in a collaborative project that is between currently Lamont and scientists at the Sandia National Labs are that if a set of templates is built, for example, on the order of 500 templates, and one tries to use them as a detector, is it within modern computational capability to search for a small array? Well, it turns out that there's nothing really very difficult about these numbers here. To search for a few years, 3 years, with 500 templates, to do that in less than 3 days. So the question then is, so many studies have demonstrated the merits of these modern methods, measuring arrival times by cross-correlation, relocating many events at the same time. And this third feature, as I've tried to characterize it in the last few minutes, is just beginning to be applied. And will it work on regional scales across broad areas? I think there are indications are that that it can. It won't ever replace, at least not in the foreseeable future, the excellent current methods, but it's always good, especially for the specialized problems of handling large amounts of aftershocks, to find ways to quickly detect, using waveform cross-correlation methods, the occurrence of new events. And in my opinion, we can do this if we so choose. So, to summarize on seismic monitoring, I've given you 2 broad reasons. It's given us basic information on the nuclear weapons development of potential adversaries. Today, it is still important as a support for a major initiative in nuclear arms control, the CTBT, although that treaty is not yet entered into force. Monitoring involves many steps. And I think you may have found in the last few minutes that the story I've had for you is a mix of very general issues about the way all of seismology has changed in the last 50 years, and then some highly specific issues, such as the merits of a particular spectral ratio. So we're moving towards the end here. I have no idea who's been listening to me. Quite disconcerting to sit in a room and not have that audience reaction. I don't know if most of you listening are students just starting out, or if there's a fair percentage of experts listening. Anyway, feel free to send in questions, a softball or hardball, and I'll try to respond. Over to you, Handy.
Okay, great. Well, thanks a lot, Paul. Appreciate the talk. Yeah, so I think there's a broad spectrum of people in the audience, so I would encourage everybody, as Paul said, to submit questions as you have them. I have a couple in the queue already, I think. Okay, so yeah, there was sort of a technical question from William Harbert. Could you show the URL for the website at Columbia? I think it went by a little fast and he didn't get it.
Yeah, you might say to people how you're going to post this thing subsequently. But,
exactly, yeah. So everything here has been recorded, and I'll put that up on YouTube probably within the next day or two, and that'll have the entire talk preserved there. We're also going to link a couple, Paul, you showed some images from a special events page that Iris had put up following the North Korea event, and so we'll link that on there as well, along with the nuclear test video. That's a pretty iconic compilation.
Yeah, I'm not finding it immediately. I'll look at it shortly. There we go. There we go.
Yeah, okay, so there it is, William.
And it is a live link, so if I do this, yeah, so here it is. So if I update it, let's see, I'm looking at my watch now, and on UTC, we're coming up to, let's see, this is 1950, I think. UTC, is that right? 16. Anyway, so the last event shown here occurred at 1842.
Wow.
So this is a live bulletin. This is work of Felix Waldhauser and David Scharf, and that would be an event that is the Bay Area south of that. So you see here the concept that here is a bulletin location. Here on the scale where this would represent about 20 kilometers north-south, 40 kilometers east-west. So these are the stations in that general vicinity which have data from events near this latest event, and in a completely different map scale. Here now you see just plus or minus 2 kilometers east-west and north-south. That event is located by the methods that Felix and David have developed relative to the location of events in the archive that are already well known. They're in the archive in two senses. This is an archive of a set of well-located previous on the order of 450,000 events for the region, but for those events, their phase picks at all these stations, and in many cases, their digital waveforms are available. And wherever you see an orange, that means that the latest event, which occurred less than an hour ago, has had its waveforms cross-correlated with the events in the archive. And in this particular case, that event was slightly moved about half a kilometer.
Awesome. Well, yeah. So I'll go ahead and post a link to this site directly on our webinar page as well, since I think it'll be of pretty significant interest. So another question is from Grald Bodden, and Grald's question is: are there any non-seismic approaches that show promise for monitoring tests as well?
Oh, numerous. Yes, I was not my brief to discuss other technologies, but indeed they are there. Let's see. I'm looking at my list of yes. So let's see. Yes, here we go. Here it is. So the number of technologies differ depending on the environment. So if we have the environment in 4 columns here: underground, underwater, atmosphere, near space. The 4 technologies listed in red are the ones used by the International Monitoring System, and seismic is recognized to be one of the most important. But also, to answer his question, radionuclide, hydroacoustic, and infrasound are used. And of course, satellite imagery can be used. Electromagnetic pulse and other electromagnetic methods can also be used. And for a number of important reasons, the radionuclide technology is profoundly important. It's a very sensitive technology. And there is a range of sizes of explosion which can be well monitored seismically, but about which there can be also some doubt about whether they might be chemical explosions or not nuclear. Above a certain size, it's not practical to think of a chemical explosion. But certainly there is a range of monitorable explosions, single-fired, one bang, not a ripple-fired explosion, but that could potentially be just a single-fired chemical explosion. And for such possibilities, the radionuclide technology is profoundly important.
Okay. Next question's from Chuck Langston. Chuck is asking: the level of research support has decreased substantially over the past 10 years for verification research. Do you see any positive developments for reversing that trend?
I'm not particularly an expert on that subject. I have to broadly agree with Chuck Langston. Um, I don't think we could have expected that the level of funding as it initially was, beginning in about 1959, at the level of 20 million a year just for the US community, which continued for decades, would go on indefinitely, because in the end, other vastly important reasons to conduct broad-based research emerged, and the burden upon the monitoring agencies of having to support truly basic research became much more shared, with agencies more geared towards studying earthquakes and earth structure, NSF and the US Geological Survey in the United States. But now, just in terms of the not so much basic research, but practical aspects of research. For example, to conduct massive tests with very large data sets to see if some of the methods that I mentioned at the end, large-scale cross-correlation studies, are practical, to find out in practice what phases should be used, to find out what frequency bands are most appropriate. To work through those details, I have to say that the work would go along much more effectively if funding levels had not suffered the decline that in fact they have over the last 10 years.
Okay. Next question is from James Nee, and James's question is the land, and this refers to actually the landslide at the mine in Utah. Why did that landslide generate the 3.6 kilometer per second group velocity LG wave rather than something that's more fundamental mode surface wave?
Well, I'm not saying that it didn't generate. Let's say those are two different terms. I mean, an LG wave can be regarded as a sum of modes, as Jim well knows. So the parameter that characterizes the strength of a source of that nature is not your typical moment tensor type of source. It's a force source in which the amplitude characteristic of the source is measured by the mass and the distance through which the center of gravity of that mass moved. So that's the overall strength parameter. And I mean, it did generate long period waves in the band, 25 to 75 seconds. So I'm not sure if I've answered Jim's question. The data is in that band from 25 to 75 seconds.
Okay. Yeah, if he has a follow-up, I'm sure he'll add it into the window. Next question is from Paul Earl, and Paul is asking if you've done any work to look at the yield estimates for the North Korean explosions.
I have not pursued that myself. I have certainly read a number of carefully developed manuscripts, and I believe there's a forthcoming paper in the BSSA. I will note the work of Jack Murphy and his colleagues, who have an extensive series of technical reports and manuscript. I think it's been accepted, but I'm not sure if its current status, if it's actually in press. That report for the 2006 event, the best estimate of 0.9 kilotons, and for the events of May 25, 2009, I believe it's something like a bit less than 5 kilotons. And then in these estimates, one always wants to know what level of uncertainty is associated with them. And the parallel question is, well, what depth did they occur? Because to the extent that one has high confidence in the estimate of depth, one improves the confidence in the estimate of yield. A deeper explosion would be associated with a smaller seismic signal if conducted at the same yield, but deeper and deeper and deeper. So There's uncertainty associated with these yields, but less than a kiloton slightly for the first one, on the order of 4 to 5 kilotons for the second one, and the seismic signals for the third one are on the order of roughly 3 times larger. So roughly speaking, that much larger for the third one of this particular set. Uncertainty is associated with what depth were they conducted at.
Okay, great. The next question is from Patrick Taylor, and Patrick is asking, there was a quote-unquote event in southern Africa in the late 1970s that was not certain whether or not it was a nuclear test or a large electrical storm. Was this question ever resolved?
Well, it was resolved in the minds of a number of participants of the studying of those signals, but unfortunately, you can't say it was a consensus. So one group is very firm in its belief that this must have been a small nuclear explosion, probably conducted low down in the atmosphere. And it's my knowledge, certainly, that a number of others are absolutely adamantly sure that no, nothing happened. So I don't say we have a consensus on that one in answer to the question, but perhaps for present purposes, it's so important to say that the assets for monitoring that part of the world today, what is it, 34 years later, are just not comparable. I mean, we just do so much better job of monitoring on a global basis today compared to September 1979. That's an interesting month. In that same month, 2 other strange occurrences. There was a very small Soviet so-called peaceful nuclear explosion conducted in that same month, September 1979, in a mine in Ukraine, which was not known about until many years later when it was announced. And a search was made in the NORSAR archives, and actually an automatic detection had been found for that signal. Also in that month, China has come up with a formal list of all its nuclear tests. And in that same month, there is listed a test for which I am not aware of any signals, but a recent book has said that it was a small atmospheric test and the parachute failed to open. So there's an interesting history here. In that month of September 1979, 2 tests, but today we're in so much better shape. So I think to the extent that there was not a consensus on the September 1979 event, just offshore from South Africa was the claimed location, was one of the drivers in seeing a radical improvement on the ability to monitor the southern hemisphere, which capability we now have.
Great, thank you. I'm down to the last couple questions, so if anybody out there has another one, please feel free to submit it whenever you get the chance. The next question is from Ilya. Oh, Ilya, I'm probably going to say your last name wrong, but Ilya Udovchenkov. And he's asking, which type of explosion is more difficult to detect with the current system? Those conducted on land, parentheses underground, or those conducted in the ocean or under the seafloor? Thank you.
I would say that the most challenging environment is to monitor underground on land. Explosions in the water column, it's been known for decades that even a kilogram, okay, that's 1/millionth of a kiloton exploded in the water column can generate signals just that traverse the whole width of a major ocean. So when you look at the maps of the detection capability using hydroacoustics, explosions in the water column are certainly well detected. Under the ocean floor, well, if that's very shallow, just offshore, then the logistics might not be so difficult, but in practical terms, that would be similar to monitoring continents. But when we speak of the deep ocean, which is the largest areal fraction of the total ocean, then the logistics of doing anything in the deep ocean, I think, regardless of the monitoring issues, I mean, it would have to be a major program of work just to actually conduct something under the floor of the deep ocean. So, to summarize, I think the underground on continents is the most difficult environment. In the atmosphere, there's very effective building up to 60 infrasound stations operated by the International Monitoring System that does its work down to well below a kiloton in its detection capability.
Okay, great. And I think this is our last question then. This is from Mohsen Faroki. And Mohsen's question is, he says, thank you for your presentation. I wanted to know how we can achieve high precision location for events with regional waveforms. Is the velocity model, does that have a large impact on location? Does it need a 3D velocity model?
Well, it's a good question, hard to give a short answer to. The current procedures that seem most effective can go ahead without the need for a very good 3D model. I mean, it helps to have a reasonably good 1D model, but certainly a 3D model is not essential, provided it's acceptable to end up with a set of events whose relative location is accurately known. Now, for many purposes, for studying earthquake physics, for example, to study the relative effect of one earthquake upon its neighboring earthquakes, it's the relative location that is all that matters. For purposes, certainly, of interpreting a particular candidate event as an explosion, we need the absolute location. So I think the most effective package of procedures is to work with these methods that give very good relative locations and think of them as points on a rubber sheet, which is stretched slightly in possibly unknown ways. But then we work with the concept of a separate set of so-called ground truth events, a subset of events who, for a variety of reasons, we have high confidence have locations that are accurately known, say to within a few kilometers. In that sense, we can nail the rubber sheet down at those places, and all the events on that rubber sheet that are somewhat near the event whose ground truth is known get promoted from being relative locations to absolute locations. So that is the way in which certainly a lot of research is going currently in seismology. It's always good to work with improved 3D Earth models, but just having a really good 3D Earth model is not the end of the game of location, because even if one did have that good 3D Earth model, there's still the question for a small event of it generating a complicated signal, and its first arrival time might not be so easy to pick. So it's these methods that work with whole waveforms and simply compare waveforms empirically between neighboring events that seems to be the most potentially fruitful area of substantial improvement over the next 10 years.
Okay, great. I have one more question that we wanted to add in. This was from Ray Williman next door in the IRIS office. We're wondering what you see, if you see any use in a proposed global array of wide aperture broadband arrays for looking at explosion monitoring. I mean, this is something that's been discussed recently within the IRIS community.
Well, you know, global arrays, that's good. I have nothing against them. I would think personally that as a priority specific to achieving progress in even better monitoring capability than we have today, which is already good, one might simply work with a subset of stations that have already built up a really good, let's say, on the order of 20-year or longer archive of high quality signals. Now, they could exist. There's a number of these stations which themselves form a global array and go back to the era of active weapons testing. So I say yes, of global array studies. I think that they have a lot of potential for elucidating deep Earth 3D structure. But for purposes of doing the routine work of event locations and so on, global arrays, I don't know, the challenge always in monitoring is to do the small events. And by their nature, small events are going to generate signals of high signal to noise ratio, typically only at some subset of the global list of stations, and specifically regional signals. And continuing to understand them would be a higher priority for me.
Okay, great. Paul, I didn't mention this at the outset, but you're presenting at your computer. You didn't get to see all the nice notes that people had sent into the questions window as well. So it's hard to get a round of applause when you're doing a webinar, but there were a nice number of thank yous in the window. And there's a few more people messaging the word clap. So yeah, but thank you very much,
Okay,
Paul.
thanks, Andy. I love all this stuff, but that's fine. And thanks very much for your help in putting this all together.
My
Thanks.
pleasure. Well, yeah, thank you again, and thank everybody else out there who was able to attend today. We'll have this archived and posted in the next day or two off of the webinar webpage, and the next one will be in a few weeks, and I'll send emails out about that. So, Paul, thank you again. Enjoy the rest of your day, and we'll see you all here again next time.
Thanks, Andy.
Yep, bye-bye.
Mhm.